Hey there, data nerds and tech wizards, and everyone who tuned into this podcast wondering what in the world reinforcement learning even means. Welcome back to Data Science at Home, the only podcast where we have a lot of coffees, a lot of GPUs, and also a good amount of sleep. Doctor says it's good, so I'm gonna say it now. I'm your host, Francesco, podcasting from the freezing office of Brussels City in Belgium. And today I'm diving into quite a controversial topic that, might just spark a debate in your next team meeting. And by the way, let me know how it goes. I'm really curious about that. So here's the headline. Reinforcement learning is dead. Yep, I said it. No take back. So, of course, don't close your Jupyter notebooks just yet. We are not here for that. We are here to celebrate the new king of machine learning. So I guess we need some drum roll. What do you think? Well, drum roll, please. Transformers. Yes, that's the same tech that powers ChatGPT, Bard, and probably the best predictive text on your phone and whatever other device you have, especially for those who operate with social media. So grab your coffee, chai or matcha or whatever fuels your neurons, just not wine, and let's break this down in the nerdiest and most fun possible way. So let's start with a quick trip down memory lane, as people say. Reinforcement learning, or RL, as I've heard the cool kids calling it, was once the golden child of artificial intelligence. And I'm saying that, back in 2016, if I'm not wrong, when AlphaGo could beat, for the first time in history, a certain Lee Sedol, well, whatever, a man, a human, in fact, playing Go, reinforcement learning back in the days was, something like, how can I say, the Beyoncé of machine learning. Now, everyone thought it would revolutionize the world. And so people were saying, robotics, reinforcement learning, solved. Medicine, piece of cake. Stock market, easy peasy. Now, fast forward to today, reinforcement learning is just, that startup that peaked too early. It crushed it in, toy problems and especially video games, as we're gonna mention later. But when it comes to real-world applications, not so much. And why is that? Is because reinforcement learning is just like trying to teach a toddler how to walk by yelling, "Good job," or "No, bad job." And every time the toddler takes a step, he or she receives a penalty, also called negative reward, or a cookie, which is the positive reward. Now, or usually a candy. Toddlers cannot even read cookies. So, to be serious now, it's inefficient, it's messy, and let's be honest, it's also a little frustrating. Not so much for the toddler. Actually, for the real toddler, yes, it could be, but definitely for the researcher or the practitioner. And of course, don't get me started on the technical jargon. If you ever opened a book about reinforcement learning, you will start reading things quite, weird stuff like actor networks, critic networks, Q values. And don't let me start on the clipped surrogate objective functions, which I really don't know what the hell is that. It's like reinforcement learning just came with its own secret language that nobody wanted to translate. Now, here's the kicker. While reinforcement learning was kind of busy overcomplicating things, guess what? Transformers came in like the chill, efficient coworker who actually gets things done. And suddenly reinforcement learning doesn't seem to be that shiny anymore. So let's talk about transformers. Of course, not the robots in disguise, although that would be cool, but the AI architecture that's really taking the world as a storm. So what makes transformers so special? Well, they're simple. I mean, that's a fact, okay? Well, they're simpler than, of course, a reinforcement learning architecture. And I'm going to spend some words in a minute. Once you wrap your head around the attention mechanism, which, by the way, is not as scary as it sounds, that's basically it. You're set. So here's the beauty of it. Transformers do work because they are simple machines. Now, the game changer is something called the decision transformer. Think of it as a reinforcement learning's cooler and more efficient cousin. Instead of running around trying to optimize a reward function like a headless chicken, the decision transformer reframes reinforcement learning problems as, I'm saying it, sequence modeling problems. Okay? Here's the trick. Transforming the problem, pun not intended, into something that the decision transformer is actually good at solving. And these are sequence modeling problems. Okay? One of the fewest reasons why transformers actually work very well with text is because text is a sequence of characters, a sequence of words, or a sequence of tokens. Doesn't matter the resolution where you are seeing it, it's a sequence. Okay? And transformers are great at that. So basically it's like saying, hey, transformers are really good at understanding sequences. So what if we just made reinforcement learning into a sequence problem? Well, when you do that, it works. Now, there is no messy multi-network setups. There is no hyperparameter voodoo or whatever. There is just one network that works. Now, here's where it gets even cooler, because decision transformers aren't just good. In some cases, they also outperform reinforcement learning algorithms. And they're also easier to implement. Of course they are. Even though, to be fair, it's also easy now to implement a reinforcement learning architecture just because these are things that are so mature. There is a lot of code base. There is a lot of code, in fact, and libraries that are very efficient, very well written. And so you can also implement a reinforcement learning strategy overnight, kind of. But there are problems when you do that in the tuning and, in praying the gods that things go as expected. Now, of course, nothing is perfect, except maybe a well-trained transformer on a Friday afternoon so that you can enjoy the weekend. Decision transformers have their limitations too, obviously. They are mostly used offline for now, meaning that they are better for analyzing historical data than for making real-time decisions. But the research is moving fast, and some folks are already working on making them work online. And honestly, I'm really looking forward to it because I believe that's going to be a very powerful combination. If someone finds a way to adapt, the concept of transformers to online learning, I think that's going to be a game changer. So what does this mean for us? Well, should we throw away reinforcement learning textbooks and start from scratch from transformers? Not really. Reinforcement learning still has its niche because there are areas like robotics, for example, where real-time interaction with the environment is very important. Environments can be very dynamic, but for a lot of other applications, transformers are indeed stepping in and proving that sometimes simpler is smarter. In fact, not just sometimes. In machine learning and artificial intelligence, almost all the time, simpler is smarter, especially when it comes to massive amount of data. You really don't want to, play with very massive models or very complicated models. You try to simplify things. So let me break it down by, focusing on the key differences between traditional reinforcement learning and the newer decision transformer. And this is going to be the serious part of the podcast. We have been, joking so far. All right, so let's get serious. Reinforcement learning, how do they approach the problem? Well, reinforcement learning is pretty much built around the concept of trial and error learning. Okay, we all know that. So it uses rewards to guide an agent toward the best possible action in an environment. So for example, if an agent performs an action that achieves a goal, it gets a positive reward, and if it fails, it gets a penalty. I'm oversimplifying here, but that's indeed what it is. Now, the goal is to maximize what they call cumulative rewards over time. Okay, and usually these things are formalized as mathematical objective. There is one thing that you really have to pay attention to. It's called the Bellman equation. That's like the core of reinforcement learning algorithms. Now, decision transformers, how do they approach the problem? Well, decision transformers treat the same problem as a sequence modeling task. That's what I already mentioned, and now we get into some details. So instead of directly optimizing rewards during training, decision transformers are trained on past trajectories of states, actions, and rewards. Okay, and I want you to focus on this concept of SAR, if that helps, memorizing states, actions, and rewards. These things are sequences, okay? They are now interpreted, they're in fact trajectories of states, of actions, and rewards. So a trajectory is essentially a history of what the agent did, of what it experienced, and what it earned, okay? The reward. Now, by using these trajectories, decision transformers can predict the next best action using this powerful sequence parsing capability of transformers, indeed. So that's why decision transformers is because they use the concept of transformers applied to trajectories, applied to sequences to get the best decision. Decision transformers. Now, about the core architecture, reinforcement learning typically uses 2 or even more neural networks. Generally speaking, you will see an actor network, which suggests, for example, the action to take in a given state. And then you have the critic network that estimates the value of a state or the expected reward of an action. Okay? It's like how good it was to perform that action in that particular state. That's what the critic network does. Now, this multi-network setup can be hard to train, and especially to debug, because of this interplay between these components. And usually, especially with deep reinforcement learning, these networks are neural networks themselves, right? Let's see how decision transformers solve this. So what's the architecture of a decision transformer? I guess you know it already. They use a single transformer network. So the transformer takes in sequences of states, actions, and rewards as input and outputs the next action. That's it. Now, the simplicity of using one architecture avoids many of the pitfalls of reinforcement learning. For example, instability in the training dynamics. There is an unstable training dynamics in reinforcement learning, which is no longer present for decision transformers. Which brings us to the training process. Reinforcement learning requires real-time interaction with the environment. So there is this agent that acts, receives rewards, and adjusts the policy in order to improve future actions. This process is computationally very expensive, especially for the environments where rewards are sparse or delayed. Reinforcement learning is also sample inefficient, as researchers say, meaning that it needs a lot of data to learn effectively, right? In contrast, decision transformers are trained offline, using pre-collected data from past interactions or trajectories, as I just said. So once trained, the transformer can infer actions without interaction with the environment because it's no longer needed. And this makes decision transformers much more efficient for scenarios where collecting real-time data is difficult, expensive, or even prohibitive in many scenarios. I want to spend a few words about the flexibility and the simplicity of this new method. Not so new. The paper is like from 2021, if I'm not wrong, and I'm going to report it in the show notes of this episode on the official website, datascienceathome.com, as always. Now, when it comes to reinforcement learning, speaking of flexibility and simplicity, reinforcement learning is definitely highly flexible. It's definitely more flexible than an offline method, for sure, like decision transformers. It can also handle online learning, so real-time updates, and environments with dynamic changes. But reinforcement learning is notoriously complex, as I said, to implement and to tune. Not so much to implement anymore. As I said, there are very good libraries, and I'm going to report some that I know from my experience in the show notes of this episode, but it's relatively simple now, like as not as it was like 10 or 15 years ago when you had to implement your own, and that was a mess. Now, reinforcement learning is complex to implement. It's complex to tune, in fact. It's, for example, very sensitive to hyperparameters, which can be extremely frustrating for a researcher or for a practitioner. And it's also very hard to debug when things go wrong. If you ever played with reinforcement learning, when it comes to tiny problems, it's even fun to see how the model is learning something in exploring the environment. But when the environment becomes more and more complex, things seem to go smooth at the beginning, then they kind of randomly go banana. So it's very difficult to debug, really. Decision transformers are easier to implement and definitely to understand and definitely to explain to your neighbors or to your grandma, especially if you're familiar with the concept of transformers already in natural language processing. They are more robust to unstable training and less reliant on complex heuristics or hyperparameter tuning. Current decision transformers are better suited for offline learning, and I want to stress on this. Offline learning is not meant to play with dynamic environments, okay? But as I mentioned, there is research, very, very novel, very, cutting edge, to make them useful in online settings. To the best of my knowledge, I didn't see any, important work so far, but I'm confident and positive that these things will come, because in my head, it's kind of the next natural evolution of machine learning. So to summarize a bit, as a practitioner, which method would you use when? So the real world use cases, right? Reinforcement learning is best suited for tasks requiring real-time feedback, as I said, and learning from interaction. That's very important. So think about robotics, navigating environments, picking up objects, but also video games. There are examples, and the first examples from DeepMind, where machines playing games, video games like AlphaGo, Dota 2, for those who remember. Reinforcement learning is also good for control systems like autonomous vehicles. I've seen some autonomous vehicles being trained with reinforcement learning in simulation, and then these trained agents, driving cars, driving vehicles in the real world. And definitely there was someone the other side of the planet praying the gods that they always performed as expected. Jokes apart, decision transformers shine in tasks where a history of data is available, and that's the biggest limitation in my opinion. And so this history of data can be used, in fact, to train the model. Now, offline problems, recommendation systems, simulated environments where there are pre-collected trajectories, video game bots trained on recorded gameplay, for example. Imitation learning is another thing where you already have let's say, the happy path of how to solve a problem, and you train a machine to replicate that behavior under similar scenarios. Sequential decision-making tasks with sparse rewards. There's another thing that is very important in reinforcement learning, is designing the reward function. That's something, it's kind of an art, a dark art. In fact, it's very difficult. It's because there are heuristics involved. There is not so much science, to be honest, behind the reward function design. So that's where the most of the creativity of the designer is indeed spent. So to conclude, reinforcement learning, of course, is not dead. That was just a clickbait. Welcome. But it's definitely taking a backseat. And in my opinion, transformers are just driving the car these days, blasting their favorite playlists and looking, super cool while doing it. If you're a data scientist, researcher, or just an AI enthusiast, here's my challenge for you. Take a look at the Decision Transformer paper. It's a fascinating read. It's from 2021, already 3 years and more. I think it will inspire your next big project, or just, teach you a lot of the things that you are using today. And that's incredible that 3 years ago, in this type of fields, 3 years is kind of eternity. That's a powerful tool and a powerful approach that we are still treasuring, we're still using so much. And it's pretty much everywhere. So definitely let me know what you think. If you are Team RL or Team Transformer, or you're just here for the memes, whatever, you let me know on X, LinkedIn, of course, on the YouTube channel. Please subscribe. That means a lot to me and to my team. We would really appreciate if you put a like somewhere. So, of course, you can engage with us also on Discord and have a chat with the team and with myself. Thank you so much for your time. I'll speak with you next time.